All right, the last question says he lifts the box with a constant velocity of 9 meters per second. Would the force be more, less, or the same if he was to lift the box with a constant velocity of 4 meters per second? The key word here is constant velocity. Constant velocity. What do we know? What do we know about constant velocity? Our net force is equal to 0 in any scenario of constant velocity, which means it's the same, right? The force he's applying would be the same, regardless of the velocity, right? Because anytime we have a constant velocity, our net force would be the same, okay? All right, now we're going to move into forces that move in 2 dimensions, so forces at an angle. But if we know anything about physics, it's that, what do we know about things that happen at an angle? Can we break them down into x and y? Because can we ever solve x and y in the same equations? No, we can't. We have to analyze our vertical and our horizontal motion completely separately. So we're going to start breaking down these vectors into 2 dimensions. Okay, this says he asked Billy if he can help lift one of his favorite boxes up a hill. The box is 1.3 kilograms. He is exerting a force of 7 newtons. This is 7 newtons. And F2 has a magnitude of 11 newtons. This one is at an angle of 20 degrees with the vertical. Do you know what that means, with the vertical? So it means here's our vertical right here. 28 degrees means from the vertical. So if we said we had an angle from the horizontal, here's our horizontal right here, so it would be that angle right there. Do you see how that's worded? Okay. So from the vertical represents 28 degrees right there. At what angle with respect to the vertical should Billy exert his force if he is to accelerate the box straight upward? Okay. So let's go ahead and draw out our diagram here. Okay. We have what other force acting on our box? Gravity. We have gravity. So we have the force of gravity. And they want to accelerate the box. So that means our net force will not be equal to 0. Okay, our net force will not be equal to 0. They want to accelerate the box straight upward. So what does that mean in terms of the x components of each of these boxes? They would, if I want to lift the box straight upward, I don't want the box to come upward at an angle, either direction, which means my x components need to cancel each other out. Do we see what we're talking about there? Right, my x components need to cancel each other out. So if I am looking at my x components here, I want to make sure that these are congruent. Okay, do you kind of see what we're talking about there? So in order to do that, I need to solve, right? I know the hypotenuse and I know the angle of that triangle. Do you want to redraw that, or do you have a pretty good picture of what that looks like? Are we okay with that? This would be called F2x. Okay, so to solve for F2x, I would take the hypotenuse, which is 11 newtons, and then would I use sine or cosine to find my x? Sine of 28 degrees. So 11 times sine of 28, and I get 5.16 newtons. And so that automatically means that my x component over here needs to be 5.16 newtons also. Is that making sense? Okay. So if that's the case, now I have the opposite side and I have the hypotenuse side of this triangle. Can I go ahead and solve for the angle now? I can. Okay. So if I have the opposite and the hypotenuse, what should I use? Opposite and hypotenuse. I should use sine. Sine. So sine of theta equals opposite over hypotenuse. And if I want to solve for the angle, I'm going to use second sine, aren't I? Inverse sine. So second sine of opposite over hypotenuse. And I get a theta angle equal to about 47.5 degrees from the vertical. Okay, is that making sense? Okay, the tough part about that problem is that we had to use context clues to understand we want it to accelerate straight upward. And so that meant that our x components had to cancel each other out. That's a tricky part of that one, okay? With what acceleration does the box rise? So let's go ahead and look at our vertical situation now, right? We know that vertically, how many forces do we have acting vertically here? I think we have 1, 2, 3. Right? I think we have the y component of each of our lifting forces and gravitational force. Would we agree with that? So we want to know the acceleration. So I want to go ahead and write out, let's do part B down here. Our net force equation for our vertical system would say F1y plus F2y minus the force of gravity. Okay, are we seeing where I'm getting those components from? Right, the y component of each of my lifting forces minus the weight of our system. So let's go ahead and solve for what is the y component of our triangles. Do I need to redraw the triangles, or do you want me to get rid of some of that writing? It's kind of tough to see there. Let's redraw our system down here. Here's gravity. Here's the first force. Here's the second force. Seven newtons. This is 28. No. This is 47.5 degrees. This is 28 degrees, 11 newtons. So I need to solve, I didn't do this correctly. Let me do this. Those two do not have the same vertical component. So I can't look like they share because they don't. 7 newtons, here's its vertical, and 11 newtons, here's its vertical, right? They do not necessarily share the same vertical component, and I didn't mean to draw it that way originally, so sorry about that. Okay, 28 degrees, 47.5 degrees. All right, so to solve for F1y, I would take 7 times cosine of 47.5. And I get 4.73 newtons. And for F2y, I'd be solving this side right here. So I'd take 11 times cosine of 25 degrees. And I get 9.97 newtons. Did those numbers kind of match what you guys had when you solved those, or am I moving too fast? It's 28. Ugh. You're right, thank you. Yeah, you're right. I just couldn't read my own writing. This is 28 degrees. So 11 cosine 28. Thank you. 9.71. Is that better? Okay. Sorry about that. 9.71 newtons. Okay. So is that what we had? Okay. So now I have net force, right? What do we sub in here for F net? Mass times acceleration equals F1y, 4.37, plus 9.71. Why am I adding those together instead of subtracting them? They're both going upward, right? They're both going upward. So I take all my upward forces and they're added. My downward forces are subtracted. Then what's going to be my force of gravity here, or my weight of the box? 10 times the mass. It's not just little g. It's not just the acceleration due to gravity. It's mass times little g. So that would be 1.3 times 10. Okay, that's a really common thing, but the force of gravity has to be the mass times little g. Okay, so I got 1.3a equals 4.37 plus 9.71 minus 13, 1.08. And I'll move that 1.3 over and I get an acceleration equal to 0.831 meters per second squared. Thank you. I'm just having a hard time with my numbers today. Okay, wait, but, okay, all right, let's try this again. 4.73 plus 9.71 minus 13, 1. Okay, I see what you're saying. So 1.44 divided by 1.3 gives me 1.11. Sorry about that. Goodness, okay. So the last question says, if Billy starts to lose focus and the angle of F1 starts to increase. So the angle of F1 starts to increase. How will the box start to move? Will they still be lifting it straight upward? Which way will it start to lean?
Left.
Toward Billy or toward the other guy?
Billy.
Toward Billy, right? That angle would get bigger, which means the x component of that angle now gets bigger, right? So it starts to come toward him. What would be true about the vertical component of his force then? It would decrease, so the acceleration would lower, right? The acceleration would come down there. Do we see how that works, right? The box would end up coming a bit further toward the left. Okay, they're pulling the boat through a dock. One pulls at 130. The second crewman pulls at an angle of 45. With what force should the second crewman pull so that the net force is the forward direction? So we want it to go straight to the left. Okay, so why don't you try this one on your own? I'll give you a couple minute head start here. Make sure we understand that the x components of these are not the same. Right? This is not the same component for each of those triangles. Right? I had to ensure that the y component of each of these was going to be congruent so that it moved straight forward. The normal force is abbreviated F with a capital N. Okay, this is a really common force, right? And it's one that we need to label correctly. FG is kind of a non-negotiable for its label, and FN is not non-negotiable for its label. Other applied forces kind of get some wiggle room about what we call those. But this one is a must. It must be labeled FN. And the normal force is the force exerted from the surface of an object to the object it's contacting. Okay, so it is perpendicular to the surface of contact. Perpendicular to the surface of contact. So if an object is resting on a table, there is a force being exerted upward from the table to the box. Okay, and that just keeps the box from falling, right? It's kind of counteracting gravity. However, the normal force is not always equal to gravity. Not always. Okay? If an object's perfectly at rest and those are the only two things acting, then yes, the normal force and the gravitational force would be equal to each other. But if there are other things happening to that object, the normal force and the weight force are not always equal. Another scenario in which the normal force is not equal to the gravitational force are when things are at an incline, right? Gravity always points straight down, but the normal force is perpendicular to the surface. So those two things do not directly offset there, do they? Right? So there's a couple examples of this. I want you to think about this example. Okay, so the normal force of, let's look at our cart system right here. Okay, if we're looking at our cart right here, there's nothing else acting on it, right? Gravity's pulling it down. The surface is exerting a force upward on it called the normal force. So in this scenario right now, are those two forces equal? Yes, because my object's not moving and not accelerating, right? So those two forces are equal to one another. What if I do this? What if I push down? Does that change gravity? No, but does it change the normal force?
Yes.
Yes. What does it do to the normal force? Does it make it greater or less than?
Greater.
It makes it greater than, right? If I start pushing on that object, the normal force has to work harder to keep that thing up, right? And what if I do this? What if I try to lift my box? Am I making the normal force work harder or work less? Right? So my normal force would be decreasing there, right? I'm taking some of the pressure off the normal force, essentially, right? What would happen if I lift it all the way off the surface? What would my normal force be? Zero, right? Because then there's no contact anymore. It has to be contacting the surface, okay? So normal force perpendicular to our surface, and there's a lot of things that play into that. That just gets put into one of our vertical forces for the most part. We draw diagrams. All right, we've already kind of talked about how diagrams. These are what we call free body diagrams, and we talked a little bit about them in our last couple problems here, but it always shows all of the forces acting. We need to draw a free body diagram for every problem that we do. Okay, I'm going to say that most problems that we do. Okay, we need to have that free body diagram. Again, the arrows always go from the system and outward. I never draw a pretty picture, right? My thing is represented with a dot, which you are welcome to do. Okay, it can be a dot. All the forces come out from that. Okay, let's draw just a couple of these free body diagrams. We're not going to draw a lot of them. Okay, the very first one, it says a book is at rest on a tabletop. Tabletop. Diagram the forces acting on the book. What do we think? So here's our table. Here's our book. What forces do we have? Normal force, because it's on a surface, and gravitational forces, F, G. Do we know that these two forces are congruent? Yes. Yep, so I don't think it hurts for you to go ahead and draw those congruency lines just to demonstrate that, right? If we know for sure that they're congruent, I think it's a good idea for us to draw it just as a kind of a memory thing. And then when we have to draw diagrams like this on the AP, they'll expect you to draw them maybe to scale or to show congruency, things like that. Anytime you can show your understanding, it's going to be beneficial for you, right? To show that you know something is the same. Okay, a rightward force is applied to a book in order to move it across the desk at constant velocity. Consider frictional forces. Draw the forces acting on the book. Now, let me point out one thing. In our last diagram, I probably shouldn't have even drawn the tabletop because I don't want those to be confused as forces. Right? Force has to be an arrow, but I probably shouldn't have even drawn that. Okay, so I won't do that next time. All right, a rightward force is applied to a book. So first of all, my book is on, it's got to be sitting on something, doesn't it? A desk. So what does it have again? Normal force and gravitational force. And are those two congruent? Yeah, because my book is not accelerating vertically, is it? It's not even moving vertically. It's only moving horizontally. So we are applying a force to the right. And we can just call this force applied. I just say APP for applied. You could just call it force P for push. It really makes no difference what you call that force, right? It makes no difference. But we said we have frictional forces. So what direction do those forces need to go? To the left, right? They oppose motion. Frictional forces always oppose our motion. So I'm going to draw my frictional force to the left. Does it need to be greater than, less than, or equal to my applied force? If I'm moving at constant velocity, what does that mean about my rightward and my leftward forces? They are equal to one another. So force of friction is F, little f. That's force of friction. That's how we demonstrate that. And we said that our push force and our frictional force are congruent. So can I just do this? Yeah, I need to do two lines because I don't necessarily know that they're congruent to normal force and gravitational force, right? I know my horizontal are congruent to each other, and I know my vertical are congruent to each other. I don't know that they're all four congruent. Does that make sense? Okay. All right, I'm going to move us on here after this one. Okay. Let's try this one here, and then we'll maybe call it. Okay. Billy is tired of his, yeah, no kidding. Okay. In the middle of a cold winter night, he decides to steal all of the boxes. Why does it have to be winter? Okay. Each box has a mass of 5 kilograms. In scenario A, he pushes down on one box with a force of 20 newtons at 30 degrees to move it. And scenario B, he pulls upward on a box with a force of 20 newtons to move it. Ignore friction. Draw the free body diagram in each of these scenarios. So I'm going to move to the side here so we don't have to draw it over the box system here. But here's our system. The first scenario, he's 30 degrees downward. Okay, and it says our angle here is from the horizontal. So we're going to show that angle right here, 30 degrees. So that would be, we called force applied. All right, you could call it whatever you want, but I might call it force applied. What other forces do we have acting here? Oh, no. Gravity. Force of gravity. And what other force do we have acting? The normal force. In this case, are the normal force and the gravitational force equal to one another? They are not, right? Because I have another vertical force that's messing things up. So they are not congruent in this case. Okay, they are not congruent in this case. Do you think the normal force is greater than normal or less than, I shouldn't say normal, greater than usual or less than usual? Yeah. Greater than, because he's pushing downward, right? He's making the normal force work harder. Okay, so that's what my free body diagram would look like for that one. The second scenario, we're pulling upward at an angle of 30 degrees. We also have a normal force and a gravitational force. Okay, so those are what our free body diagrams would look like. This says find the magnitude of each force acting on the box. Okay, each force acting on the box. What would be the gravitational force in each of our scenarios?
10.
Yeah, it's not just gravity, it's mass times gravity. What'd you say? No, because this is the applied force. So the mass, the gravitational force is just mass times gravity. So our
there are like 4 boxes.
You're right, but each box has a mass. I'm sorry, I missed that part. Each box has a mass. Right. Okay, good. But we're gonna act like this is just one whole system. So he's applying a force to one box, but that whole system would move with the same acceleration, the same all that. Okay, that's a good question. So we'll consider that our whole system has a mass of 20 and acceleration of 10. So that would mean that we have a gravitational force of 200 newtons. Okay. So how about in this first scenario, let's go ahead and solve for what is the normal force. Let's solve for the normal force. Okay, if we're looking to solve for the normal force, does that mean, are we considering the vertical forces or the horizontal forces? What are we concerned with? Just the vertical forces. So I have 1, 2, 3 vertical forces that I need to take into account in order to be able to solve for the normal force here. Okay, so I'm going to come over here and let's look at our system a little bit better. Okay, so if I want to solve for the normal force, I'm going to put all my vertical forces into my equation. F net equals normal force minus gravitational force minus F applied Y, right? If this force right here is the applied force, I want the Y component of that, not the X component of that. Right? You don't have to write APP if you don't want. You could just write push or pull. I don't care what you write, okay? What is my net force here in the vertical direction? Is my object moving or accelerating vertically? Or is it just sliding? It's just sliding, which means my net force in the vertical direction is 0. Which means the normal force must be equal to the sum of our 2 negative forces. Okay. Gravitational force we said was 200. F applied Y, I need to solve for that, don't I? I need to solve for the Y component of that force. So I would take, if this is 20, I would take 20 times sine of 30 degrees. And I get 10 newtons. So that means the normal force in this scenario is 210 newtons. Right. And let's say if nothing else was acting here, our normal force would have been 200 because it would have been equal to our gravity. But because we're pushing downward, that we said that was going to make our normal force work harder, which it did. All right, how about our next one down here, our next scenario? Our net force would be normal plus applied Y, because they're working together in this scenario, minus gravity. Are we accelerating vertically here at all? No, so my net force in the vertical direction is 0. Normal force is what I'm solving for. Isn't my Y component going to be the same as my previous problem? Because my angle is the same and my hypotenuse is the same. So now we're just adding 10 to the normal force, or they're working together. And so that means my normal force in this case would be 190 newtons. 190 newtons. Gives me an acceleration of 0.865 meters per second squared. Okay, and I'm only focused on my horizontal there.